platforms for one of the top 10 US bank clients. So, yeah. So here's the situation I want to talk about today. Banks are sitting on some of the most valuable data in the world, and most of the people who work even can't touch it because not because of the technology, because the controls that keep the data safe also keep it locked up. So how do you unlock the data and actually get value out of it? So that's the problem I set out to solve with self-serve analytics. So the industry already solved one version of this platform, open banking. So if you want to share the data outside or to a fintech, to another institution, there's a whole playbook for that now. APIs, consent, contracts, all that works. But within the bank, it's a different story. When I joined this project, every business question turned into a ticket, a service now ticket. Someone in the branch organization wants to know how a product is performing. They file a ticket, they file a request. It goes to the central team who already has 100 of other requests sitting in their queue. 3 weeks later, a report comes back, and half the time the question has changed by then. So does the data because the data would have been updated by then. So the question we set out to answer was, can you give thousands of employees a real access to data full of personal information in an environment regulated by OCC without compromising governance? So most people assume the answer is no, but we thought of having a solution on top of it. It was a simple trick. It turns out that some metadata change. Now the core idea is just one sentence. You just need to centralize the standards, not the whole work. Most central data teams try to do all the work themselves. Every report, every transformation, every request, that becomes a bottleneck at the end. So what we centralized instead was the front door. Every data set that enters the platform passes through one ingestion contract, and four things happen right there at the gate. So the schema gets registered before any data lands. So that's the first step. And then we have the lineage that gets captured so that every field traces back to its source. And then we run the quality rules so that every column gets a sensitivity classification. Now, but once we have the sensitivity classification, we have the exact PII level of data. Now, that's the metadata. You can get you can let go of everything downstream. So business teams can transform, explore, build because the guardrails travel with the data. On the right, you can see the pattern we enforced. Raw data lands and stays untouched. Facts and dimensions from the business model is confirmed. On top of it, we have materialized views that sits as a curated query. Three layers, and we never changed the pattern. We just kept it consistent across different business domains, and this boring consistency is exactly what lit the whole staging scale. So here's the actual platform, left to right. Data starts in the system of record, core banking, payments, master data, CRM. So it flows into the enterprise data lakes, which at a bank this size means it could be Hadoop, Oracle, Teradata, a bit of everything accumulated over decades. From there, transfer jobs land it in Google Cloud Storage. We have the Dataproc and Spark that handle the heavy transformation. We have the BigQuery that holds the semantic layer I just described. And on top of all of this, we have a cloud scheduler that orchestrates the refresh cycle. On the far right, nobody requires raw tables. Consumption happens only through a Power BI, governed Power BI models. So we covered six business domains, customer, branch, deposits, and so on, with having around 3 to 5 years of history each, depending on the domain type. We use around more than a terabyte of data, and in each vertical, we had somewhere between 20 to 30 business users doing their analysis using this tool. The output landed on Power BI, but also served some native Excel users who still preferred pivot tables on the same data. One build, two audiences. So as I was saying, these are the six domains we served: the customer data, the branch, the deposits, payments, transactions, small business, and marketing. Every one of them shipped exactly two products. One, executive level dashboard for the leadership, and two, actual self-serve analytics tool on Power BI, where users change the filters themselves, pull the exact cut of the report they need. So same pipeline, same layers, same security model. The only thing we let flex was the refresh cadence. Payments and customer data ran monthly because the volumes were like too large. Marketing ran weekly because the business needed it weekly, and the volumes allowed that scenario. So here's the lesson that I would offer any team trying this. Domain number six costed us a fraction of what domain number one. That only happens when you keep the pattern consistent. We have all the semantic models consistent. The only thing was a slight change with the vertical. The moment you let each domain negotiate with its own architecture, it kind of became it. Every domain kind of becomes its own project. So a delivery method is more important as part of the architecture. Three phases. First, for each domain, we build a prototype in just 3 to 6 months of data. And this was done on a sandbox environment with real business users actually testing it. Now, once we proved the semantic model was right, as a second step, as a second phase, I would say, when the pilot was already running, we ingested full 3 to 5 years of history in parallel. Again, this work stream was in a parallel cycle. Once we got the full 5 years of history, we productionalized repointing the already proven semantic model just to the production data. Same model, we just have to repoint to the new data. The model and the data volume were never at risk at the same time. When the model was unproven, the data was small, but by the time the data was huge, the model was already validated. So now the part every banker in the room is waiting: security. So how did we make sure having in the being in the banking, the data is secure enough and the PII data is not exposed? We've set up four controls. One, the row and column level security. This was enforced in a BigQuery and as well as in Power BI. Then the second one is the PI encrypted. We kind of masked using encryption techniques. There's no report on this platform that renders the actual personal data. Third one is certified data sets. We have run through the quality and lineage guarantees. We kept that separate from exploratory environment. And the last one was the access. Access groups. So people who have specific entitlements only can access the data accordingly. So all these rules live in the semantic layer. So if a business user so that a business user want to build any report they want, they can't leak anything because the layer simply won't allow what they are not to see. Uh, how would user experience look like? So they open their domains tool in Power BI. They set the filters, build the report they need. No ticket, no queue. Analysts who want to go deeper curate with a Power Pivot, still inside the governed model. Our central team, who had a lot of queues with the tickets, has completely gone down because a lot of analysts started using this tool on their own and getting the reports on top of it. And the cherry on the ice was we added a Microsoft Copilot. We integrated a Microsoft Copilot to this. Two capabilities. Users can ask questions in plain English directly against the semantic model. For example, how did deposits move in the Northeast last quarter? So, and leadership gets an auto-generated summary of the executive report on every refresh. So they read the whole story. They just can't. It's not just about looking at the charts. So one thing that I want to highlight here is everyone right now is nervous about pointing AI at a banking data. Again, this process is safe for exactly the reasons because the AI sits on the certified mask semantic layer. It inherits the row level security. It governs self-service so that any foundation of semantic layer can't be gone out of the system. And yeah, so let me be honest about what went wrong because that's usually the useful part. The transactions domain nearly broke us. The tables were too massive, years of payment activity when users ran interactive queries against them, the cost and latency just blew up. My first instinct was more of compute. but the fix was to pre-compute a monthly aggregates and materialized views. Now we gave up on the daily grain on biggest tables so that we got back the speed, reliability, and the bill that we could predict. Uh, Sometimes the right answer is just about the less resolution chosen on purpose because it's not always about the data. So three other lessons. One was around data quality gaps. They were at scheduled risk. So the profile data before you build, we could not check that. Then the access to subject matter experts gated everything. So lock requirements down in workshops early. And the deepest one is the semantic layer. It is coming as a product, so the dashboards are just the front part. Three takeaways. One, metadata is the actual scaling mechanism. If you get the standards right at the gate, then everything downstream can be easy for you. Then we have to trust the architecture because the controls in the layer, every report inherits that architecture. And the self-service is the actual economy. Treat every data set as a governed product, and 20 or 30 people per domain start creating value without even asking anyone's permission. So open banking taught this industry how to share the data outside, but this solution made us how to unlock the data within the bank. That's it from my end. Open for any questions.
So do you use any third-party tool for your semantic?
No, everything was built on GCP.
Thank you.
Thank you. Thanks. Thanks, Joseph.
Yes, hi. Let me share my screen. Okay, so thank you everyone for uh, joining. Good morning. Thank you to the team and University of Essex. So my name is Zalak Shroff. I work as a lead database architect. Um, so in my this presentations, I will cover four things. So my topic is the data-centric approach to the proactive infrastructure management. So I will cover four things. The first one is like why the reactive model is no longer enough, what database-driven predictive architecture looks like, a pattern, a system that use it, and the result we measured. So the framework which like applies to the mobile networks, smart cities, and the autonomous vehicle networks. Okay, so the network operations have used the FCAPS model for many years, which is like fault configurations, accounting, performance, and the security. So FCAPS respond after the performance has already dropped. This is known as a break fix cycle. It is becoming less effective in 5G and 6G networks where the user moves at speed and the application works in the real time. In these conditions, small coverage labs produce drop called buffering and a poor user experience. There are two types of failures, and both are detected late. So the first one is the dark failure. The service is completely lost, and we detect it only after the loss. user experience is first, and the another one is a gray failure, where the performance degrades slowly and remains invisible until the threshold is crossed. So the problem is a trigger. So the reactive system wait for the threshold breach, or a user complaint. So at that point, the user experience has already like failed. So the log analysis after the event is useful for diagnosis, but it is cannot capture the time-based patterns that lead up to the total signal loss. So detection delay and the manual rerouting add further time. So user impact is therefore certain and it is not likely. So in all of these cases, the warning data has already been collected. What was missing was a system designed to ask like forward-looking questions for it. So this is a predictive model. Like the proactive management differs from the reactive management in the five different ways. So the first one is trigger, where the pattern matching on the live telemetry instead of the threshold bridge. The data strategies, the impact, the focus, the quality of the experience instead of the component uptime, then decisions need speed, like the automated instead of the manual intervention. So the method is to build the statistical baseline for the normal behavior through the continuous monitoring. So research using control network which identifies which metric act as early indicators. So signal to the noise ratio degradations and the jitter trends change the several minutes before the connection drops. So the process has a stage. The first is learn, predict, plan, and act. Um, so these slides cover most of the engineering efforts goes. So the main design decisions to make the database part of the predictive process rather than the passive store. So the relational databases cannot handle the high frequency time series telemetry. This is a structural limit, not a configurations problem. So we run the machine learning inside the database engine. This removes the cost of moving the data between the storage and a separate compute cluster. So the architecture uses like four components: the PostgreSQL ML in the database training and the real-time classification for the signal quality, then the MindsDB, InfluxDB, and the Redis, the vector similarity to annotate against known the coverage gap patterns. So all the components must share a consistent view of a time. We keep the state synchronized across the thousand of sessions within the 100 milliseconds. So the telemetry has a four types: the network metrics, GPS data, the user behavior, and the environmental and the sensor data. So the system act only when the statistical confidence is sufficient, and the low confidence means there is no action taken. The practical conclusion is that the choice of the model matters less than the data collection, labeling, and the joining. Um, so in this slide, I have co-invented a pattern. This pattern was granted into the 2022, which predicts the wireless coverage loss on the journey before user reaches it. The process has a four steps. So the application takes the route from the map applications onto the device, and it sends the route and the device details to the antenna radio and the model and to the coverage determination server. So the servers apply the propagation model to the network data and returns the coverage profile for that route and that device. So the application notifies the user and instruct the content application device to download before the gap. So the notifications contain like three values: time to the gap, distance to the gap, and the length to the gap. So the system does not report that the problem exit; it reports how much time remains, which we need to act. So this is an orchestration layer. It converts the database result into the automated workflow with the no human involvement. So the wider pipeline is that the lead time is to design the requirement, not the output. So every layer below it exists to produce it. Uh, so so the scheduling problem covers one day divided into the 1440 slots in of 1 minute each. So the objective is to maximize the total utility, the reward multiplied by the probability that the prefetch succeed. So the heat ratio is okay here. Yeah. So the heat ratio is like a 40% of the baseline and 52% of the generic algorithms and 56% of the memetic algorithm. There is a catch utilizations which is like 45%, for 58% and the 61% respectively. So mean time in the catches fails from the 110 minutes to the 82 minutes. A lower value is better for this matrix. It means that the content is delivered closer to the time it is requested, and the content stays current and uses the less storage on the device. So we tested intended forecasting separately using the random forest and the XGBoost. So the input are session depth and also in the viewing sequence. So across the 3G, 4G, and the 5G models, this reduced startup latency by 31% and the rebuffering events by 47%. Um, so the predictive system do not replace the reactive system. The two works together. The predictive layers manage which knows the risk and SLA threshold and slow degradations. The reactive layers handles the unpredictable events, like there is a fire cut or severe weather changes, then any physical damage. So no model can forecast this, but the confidence threshold decides which layer responds. So below the threshold, which we like control returns to the reactive layers. So this design is also avoid the like oscillations where automations that react the every change that makes the network less stable. So before any kind of deployment, define these three things. The first is like the confidence level required, which we need to add before even it lose the connection, and the maximum change permitted into the single action, and the rollback procedure. Um, so there are three stages ahead, which is like self-monitoring sensors, then automated reconfigurations, and the self-healing infrastructures. So the same architecture applies outside of the telecommunication traffic management, and also the public safety energy, gate balancing, and the public service delivery. So the practical starting point where like the select the one failure type you already understand and rebuild the whole 12 month of labeled history for it. So the data set is the lasting asset. Model can be come and go, but the data where it belongs, it very important. And the future is not the like reactive, but the proactive data centric management is required for any kind of the future infrastructure. And yeah, thank you. That is, if I'm open for the questions. Thank you.
Thank you. Can you guys see my screen? Okay. Thank you very much. And my name is Anil Kumar Bachu, and I work as a lead data engineer in BlackRock. I'm based out of like Atlanta, United States. So today I'm going to talk about the beyond the cloud AI native platforms for the future of the financial technology. So over the last like the decade, the cloud transformed the financial technology by giving it the scale, resiliency, and speed. But cloud alone is no longer a competitive differentiator. So the next wave of transformation is AI native platforms, the platforms where intelligence is embedded into the operating model, not simply added as a like the feature. So today I would like to discuss what AI native really means, why financial institutions are moving in this direction, the architecture that's required to support the yeah, and like the implications of the technology in the leadership world. Just give me 1 second. Okay. So, in the financial industry has leveraged completely, like the major, like the cloud migration, like the programs. However, AI is, like creating the new source of competitive advantage. So the focus is shifting from managing applications to orchestrating decisions or decision support systems. So instead of asking how quickly can we deploy the software, now we are asking how quickly we can generate the insight, manage the risk, and deliver the customer outcomes. So the industry is responding aggressively. The banking executives increasingly expect that AI to reshape their business models. So with cybersecurity governance investments continue to grow along the AI adoption, the question is no longer whether the organizations will use AI. The question is how they can scale AI responsibly. So there are four, like the stages of this, like the evolution. One is the cloud native, which is the modern infrastructure. Number two, the data native, which is governed, reusable data products. Third is AI assistant, the co-pilots, like the argument users, like the AI native. That means, like the agents and the intelligence becomes the part of the platform itself. So the distinction is the most important. AI assisted systems support, like the decision support system. So the intelligence becomes a platform capability rather than the application feature. Now let's look at like the architecture. Okay, so if you look at like the reference architecture, everything like begins with like the trusted data. So we then like introduced a model layer where AI models are trained, managed, and evaluated and monitored. Above that, it actually sits an agent for like orchestration layer, the the intelligent layer that coordinates the workflow. So the guardrails and governance are not, like the side functions, they are embedded directly into the platform. So observability, one of the key thing, for the data provides continuous, like the monitoring of decisions, the risk, the model behavior, and the outcomes. So the important takeaway is that AI cannot be separate from the governance. A successful AI native platform combines both. Most AI challenges are actually, like the data challenges. So organization often, focus on the models where underestimating the data quality, the lineage, metadata, and governance. So the AI native platform require four foundational capabilities. One is the product foundation, the model lifecycle management, the agent orchestration, and the policy enforcement. So as autonomy increases, the confidence in the data quality and the governance must increase the proportionally. So the future competitive advantage won't come from like just having the models alone. It will come from like governing them at an enterprise scale. So the traditional, the automation, like executes the predefined, like the steps in generally, any of the, like the programming approach. So the agentic systems can reason, plan, and coordinate the multiple tasks. So example includes, like the research assistance, operational investigation, the reporting workflows, the compliance reviews, and customer support. So the role of an employee is shift from executing repetitive steps to supervising outcomes and managing expectation. However, the autonomy must remain bounded. Every agent needs permission, control, escalation path, and audit trails. So think of an agent as an, like a highly capable digital worker operating within a clearly defined responsibilities. So there are, like six major, like the value pools or value propositions. The clients and advisor experience. Number two, the risk intelligence. Number three, operational productivity. Number four, engineering acceleration. Number five, payments and liquidity, optimization. Six is the product innovation. So the critical point is that the success should not be measured by AI usage. It should be measured by reducing the cost, the faster life cycle times, the improved customer service or the customer experience, and the stronger controls. So the business becomes, the business outcomes matters more than the AI adoption itself. So what is the most important thing in the architecture and governance is the trust. So, in financial services, the trust determines the speed of the adoption. So, the NIST frameworks like offers there are four like simple structure: govern, map, measure, and manage. So, AI introduces like the concerns around explainability, privacy, cyber security, bias model drift, and accountability. So, these challenges cannot be addressed through the periodic reviews. However, they require the continuous compliance and continuous monitoring. So the institutions that scale AI fastest will likely be those like the strongest the governance foundations. Coming to the technology, right? The technology is insufficient. So AI native transformation requires an organizational change. That means like the mindset change. The platform teams provide like the common AI services. The product team focus on the business outcome. The risk and compliance teams become like active participation in the design and the deployment. So the data stewards like ensure the data quality and the consistency. A common mistake is treating AI as an isolated innovation program. So the successful firm treats an AI as enterprise capability. So there are several trends that will shape like the next decade. So I would like to focus like the five the major development that is going to occur in the next decade or so. The real time the risk intelligence, the digital assets and tokenization, distributed and confidential AI, synthetic data and the digital twins, and the composable financial ecosystem. So each trend increase the need for the intelligent, scalable, and governance platform. So the common theme is the real-time decision making. So the future lies on the real-time decision making support systems. So what is the transition roadmap is going to look like? So again, this is my like the recommendations. Okay, the strength, the phase one should be like the strengthen the cloud and the data foundations. Number two, stand industrialize AI and model services. Number three, introduce governed agentic workflows. Number four, scale successful patterns across the organizations. So the biggest risk is that launching dozens of disconnected AI pilots that never reach the productivity, and the maturity. So the successful transformation requires a repeatable platform capability. So to close that, I will finish with like the four messages. Number one, cloud remains like the essential, but no longer isn't enough. Okay. Number two, AI platforms are built on a reusable and capabilities. So the data products, the models, agents, guardrails, and observabilities. Number three, the governance is not a constraint. The governance is what enables the scale. Number four, it begins with the business domains where value, the risk reduction and the measurable outcomes are observed. So the future of the financial technology will not be just defined by who has the most AI models. It will be defined by who can operationalize the intelligent most effectively and most responsibility and the most consistently across the enterprise. So thank you, and if you have any questions, happy to answer.
Hello, can you
Yes,
see
I
my
can hear
screen?
you.
Hello, can you see my screen? Okay. So good morning, good afternoon, and good evening. So I'm Suresh Gandhisari. I work as engineering director for one of the product company called Fire. So today I'm going to take a few minutes in terms of presenting about how the legacy enterprise legacy systems can be leveraged with AI, and especially by integrating AI into the legacy systems and leverage some of the autonomous operations that can be performed on the systems using AI. So that's the primary topic for the discussion today. So before I really get into the specifics, so one, there are multiple ways of actually looking at how you can modernize your applications or systems. One, either you can actually do a complete lift and shift, or like rip and replace, or like you can even use the existing systems and leverage and have a proper integration in place, and etc. Right. So the real advantage of having a legacy systems over a period of like 20 plus years in the market with lots of large customer base is it is actually been a system in the production for years, where it's been tested uh, with the yeah. Oh, sorry. Can you see it now? Oh, thank you. Sorry. So the advantages of legacy system is that it's been proven, it's been used by the customers, it's been large set of users, been tested with different business rules in the greenfield, and it's very difficult to replace with a greenfield model with the legacy systems. So and also one of the thing which AI agents require is obviously having the real domain context, which legacy systems have for years. And that domain context will definitely help in terms of building and delivering the reliable autonomous outcomes instead of with reducing, I would say, hallucinations. So your legacy system is not dead weight. It's a good asset for your AI integration. So the market, at least from a market study that we actually have found out, is The agentic, the AI agents and having that executed reliably well in the production environments is between 16 to 25%. So it's again, it is not about the AI agents or the AI models. It's all about how your underlying system, underlying architecture, and the way how your legacy system supports those AI integrations is the key for the failures. Like especially having some fragile APIs, and we don't have a good visibility into what's happening. So AI agents cannot even discover the issues, and also mainly missing the domain context. So what the real advantage of actually bringing the AI into the legacy systems is to really build something robust architectural system underlying, so that it can be integrated and planned and integrated really well with the AI. So there are different proven approaches. Obviously, like you have core architecture patterns, like having AI layer as a sidecar, along with your legacy system, which runs in parallel, reads with your system legacy system APIs, traps, and also various log streams and so on. That is one approach. Obviously, the second approach is like having a event-driven augmentation, where your AI systems like agents specifically read the structured events that are triggered by your system, either by subscribing to your Kafka, NATs, or any event bus, or even through REST APIs. The other approach is like building a semantic abstraction layer. Abstraction layer is like anything similar to like API gateway, but it's more of a natural language base which wraps your system REST APIs, or like is any CLI commands, and where your users, end users, can express in the plain English, and the LLM underneath, which actually is the fine tune for your system prompts, can be validated and translated into payloads. So that could be another approach. Well, now in order to do, obviously we have various enabling technologies like AI gateway and MCP protocol, where it standardizes how AI agents discover and invoke your legacy system tools and APIs, and then AI agent orchestration. So there are multiple open source frameworks and frameworks available like LangGraph, AutoGen, QUI, where you can build a multi-agent agents which actually can do a specific purposeful task. That could be a config generation, validation, execution, etc. So and now in all of this, AI gateway obviously is a non-negotiable control plane. The reason being, it is the where the security, observability, governance of all the agentic traffic are being actually observed and converged. The architecture blueprint. Uh, so I was referring to here one of the product called F5 Big AP, which is like in the legacy in the market for almost like 25 plus years, and that's where we actually have enabled the AI on those specific legacy product that was existing in place. So, and obviously there are multi-layered approach here, right? One, the end users, it could be human or any automated systems that generates the triggers or events. And then actually, it actually goes to AI gateway, and where your authorization, authentication, and your prompt sanitization and model routing, etc., and also enabling the observability on those AI agent calls and the prompts and so on can be done. And building an AI agent orchestration layer, especially like in a multi-agent framework for building the agents, and also making triaging, config generating, some of the validations, config validations, and execution of specific I rules or tasks that can be done through AI agents. And AI agents, once you have a AI gateway, AI agents, obviously, before that, we need to enable your legacy system with enabling the MCP protocol. And that's where like your AI agents can communicate with your legacy system. Here I talked as like F5 Big AP, which is basically exposes all your core capabilities that where AI agents can leverage through MCP. And underlying is where like you have a legacy system where it has its own set of architectures, components, APIs, and your telemetry streaming and etc. And with respect to have combining the legacy system and Gen AI end to end, so it's all about leveraging your core strengths of your legacy systems. It could be a telemetry ingestion layer where your all your events metrics are streamed via Kafka or to any message event bus to any different destinations, and at the same time having AI agent reasoning where it can be done via AI gateway and the MCP tool registration, where all AI agents can actually register their specific tools that are needed for from the legacy system via MCP. And obviously, overall translation of your intent to the config, right? Especially config generation agent produces validated underlying legacy system commands or payloads via agents. So all this integration, proper seamless integration by having the AI gateways, agents, and MCP on top of your legacy systems, and also making sure that your legacy system has a proper architecture to support it is the key here. And which over are doing all this, there's definitely there is an impact in terms of the business and also for the customer use cases. Like you can detect and remediate any incidents like less than 30 seconds. This is what something that we have seen. And the L4, L7 incidents and overall response rate actually have reduced, improved, and etc. Right? So it's an end of the day, not only having the AI integration with the legacy systems, you also have a proper human in the loop to make sure that some of the reviews in terms of the actions has been taken. So yeah, I think there is obviously a governance needed. So that's where like AI gateway functions and MCP protocol has certain level of governance, and the underlying product, which is like legacy product here, has its own governance, like having the proper RBAC. So it's not that all AI agents has been given all the permissions. It's basically given a minimum privilege role so that you don't have a right access on specific tasks until unless there is an approval needed. And at the same time, policy enforcement and rollback designs and everything is actually taken care by your legacy system. But the overall governance on the AI side will be actually done through AI gateway and MCP protocol. So, and on top of all, so one of the key, obviously, strategic recommendations here is when you're really looking at integrating AI into your legacy systems, make sure that your legacy systems data and the context is being taken care and to take the full lineage of your legacy power. At the same time, you also need to have the success metrics in terms of how uh, the overall AI integration is helping in some of your autonomous operations with respect to the traditional way of doing things. So that's the key here. So that's pretty much I have from my side. Any questions? Thank you. Thanks, everyone.
Yes, you are audible. Can you see my screen? Yeah, so I'll get started. So, hi everyone. I'm Milan Dudatra. I am a software developer engineer at AWS, where I work on large-scale distributed infrastructure, especially around reliability, live migration, and maintenance workflow across EC2 fleets. This talk is called "Predict Before You Repair," because one of the biggest shifts happening in the distributed system is moving from reactive repair to proactive prevention. Traditionally, systems detect a failure after something breaks, and then we try to recover. But at hyperscale, that model is too expensive, too disruptive, and often too late. Um, in my work at AWS, I've seen this directly. We build system to reduce disruptive outcomes like unnecessary eviction by analyzing operational signal earlier, making maintenance workflow more fault tolerant, and introducing safer retry and recovery paths before customer impact happens. That experience shaped the core idea behind this presentation. Reliable system should not just recover well, they should anticipate risk and act early. So in this presentation, I'll walk through how predictive failure prevent change the way we design distributed system, and what architectural building blocks make it possible, and how this idea become even more important as AI agents begin operating production system with greater autonomy. And the key message is simple: the future of reliability is not just faster repair, it's better prediction, safer automation, and smarter intervention before failure reaches the customer. Um, why this topic matters? So, in distributed system, fail in messy, partial, and non-deterministic way is very important. By the time a failure is visible, the blast radius may already be growing, and the prediction prevention reduce downtime, cost, and customer disruption. And why you are credible to talk about this um, would be like at AWS, you worked on EC2 Nitro maintenance and migration reliability. So uh, it is important to improve live migration and eviction reliability across millions of systems. In the same way, all the other companies who is working on operating on a large scale environment, they also need to make sure that their production load is, should be handled proactively. Let me go to the next try. So what I wanted to do is building a build distributed backup system and workflow orchestration. So I want to make sure that whatever happens at the backend level, I should be able to uh, maintain it. Uh, I build system that coordinate large-scale backend operation reliably, especially where retry, state transition, and service dependency need to behave safely under failure. Um, so I developed LLM-powered operation agent for live migration, where I need to make sure that uh, operator assistant can speed up failure diagnosis by correlating workflow state, log metrics, and known failure pattern, especially for live migration issues. Uh, the focus is AI, distributed system, and cloud reliability. My main interest is bringing together large-scale system engineering and AI assistant operation, so infrastructure can become more predictive, more explainable, and more resilient. Uh, the challenge. So in every uh, new things that is happening in the industry, uh, there are many challenges that we need to look after. Uh, One of them is how the distributed system failed due to a dependency failure. So in distributed system, we have like uh, many dependency around the team. We are working with the different sister teams, so we have to make sure that uh, we are in line with all the stakeholder here. Um, and distributed system fails for many reasons. And the difficult part is that failure are usually not isolated. A dependency timeout may look like an application problem, which may trigger retries, which then create a resource contention. Then there is a hardware degradation may first appear as a intermittent errors long before a host is considered unhealthy. In practice, these incidents rarely begin as a clean failure. They often begin as a weak signal, slightly elevated latency, then abnormal retry rates, noisy dependency behavior, or unusual workflow transitions. So these are all the things that happens in the beginning. What I have seen in the production is that by the time a system crosses the threshold for an alarm, the problem is often already underway. At that point, the flow becomes reactive. Something falls, an alert fires, someone investigate, and then fix is required. That process is necessary, but it is not ideal for high-scale system in this AI environment, where every minute of delay can have a multiple impact. So at AWS, I worked on maintenance and migration workflows where the challenges was not just fixing failure, but reducing how often workflow enter bad state in the first place. For example, by analyzing large volume of migration outcomes, we could see that some failures were transient rather than terminal. That kind of transparency is exactly why predictive system matters. The real goal is to detect leading indicators before customers are affected. Instead of asking why did this fail, we want system that can ask earlier, like what signals suggest this is likely to fail next. Uh, from the so I wanted to uh, think more about on a vision aspect. Um, as you can see, telemetry, AI models, failure prediction, and automation remediation. Uh, this sounds like a really hard thing to do in this AI environment because there are security aspects that we need to look into consideration. Uh, how we can involve human if AI is not able to solve the particular problem. If we are completely, uh, migrating to the AI will be solving the entire problem. Uh, so what I would be thinking here is that I have like many research things that I am operating right now: AI-driven self healing orchestration, operational intelligence, agentic infrastructure. These are all the research things that I have been working on. Um, Main outcome for all of this is to uh, somehow find out like how I can be predictive, self-healing, and um, how I can create a predictive and self-healing infrastructure for any system in the large scale distributed environment. Uh, and the last thing would be, so as I discussed earlier, reactive monitoring is all only thing that we are doing in current environment. We need to move on from it and then trying to build like how we can involve AI in this situation. Um, so today we are only focusing on monitoring, uh, creating system that can create alarm for us, and then wait until something happens. This is not something that we should be uh, doing. Tomorrow's model should be very different. First, predictive intelligence system should identify weak signal before a workflow fully fails. That could include raising retry rates, specific state machine transition failure, latency drift, or infrastructure degradation pattern. Second, AI-based root cause analysis. Instead of engineers manually piecing together log and matrix, models should help correlate events across services and narrow the likely source of failure much faster. One of the things that I see in the industry right now is people using AI to feed their documents within the team or within the org, and then uh, try to solve any tickets using the AI, and that is gonna grow more and more by AI would be taking over by solving all of those tickets by themselves. Um, the third thing is self-healing workflows. Once the system has sufficient confidence, it should take bounded action automatically. Um, at AWS, one of the projects that I was handling, it was an example of a rule-based version of this idea. The next evaluation is making those action adaptive and content aware. Um, the fourth, agentic infrastructure. Multiple software agent can monitor health, validate risk, coordinate remediation, and escalate only when the situation falls uh, outside the safe policy boundary. So the future state is not just better monitoring; it is infrastructure that prevents failure before they happens, minimizing the human intervention for common failure modes, and lets engineer focus on high value design decision rather than repetitive operation recovery. Uh, if I summarize the message in one sentence, my experience at AWS showed me that the biggest opportunity in cloud reliability is shift from reactive incident handling to predictive self healing system. And I see AI agent as a next practical step in making that possible. Um, that would be it from my side. If you have any question, I'm open to answer anything. Thank you.
Hello everyone. Hello everyone. I've shared my screen. Let me know once you guys can see it. Can you guys? Okay. Yep. Thank you. Thanks for the confirmation. Good afternoon and good evening for the people joining from different time zones and participating. Thank you so much for the opportunities. My name is Saddam Hassan, and today I'll be talking about how ML can optimize lime kiln operations by improving product quality while also reducing fuel utilization or the consumption of different emissions gases that is emitted from the kiln. So this work, what I'm explaining, it comes from the real world or real industrial experience and focuses on solving practical problems faced every day in the lime manufacturing. So the agenda, I'll begin with a brief introduction to the lime industry, what it is, and how the lime kiln actually works. Then I'll discuss the challenges, explain the different machine learning approach, and finally share the expected business impact and future opportunities in the domain. So starting with the lime industry, what actually is lime industry? So lime is one of the major industrial material. It is produced by heating limestone at a very high temperature. Although the process sounds very simple, but it requires a large amount of energy and very precise control. So even a small improvement in kiln performance can save significant fuel and improve product quality. So what are the different lime industry currently using the lime? Lime is used in many industries, including steel, mining, construction, water treatment, agriculture, and chemical manufacturing. Because it is used in so many industries, improving lime production has a direct impact on both cost and sustainability. So, what is a lime kiln? So, a lime kiln is a large rotating furnace where limestone is converted into quicklime. The process operates continuously at very high temperature, which range from around 1000 to 12 to 1300 degrees Celsius. To maintain consistent quality, operator must carefully control temperature, fuel, airflow, oxygen, and many other process variable. So it's not only a rotary kiln, there are other types of kilns as well, which does not rotate at all, which are called as vertical lime kilns. So this is the typical representation of a rotary kiln, which is a more like a horizontal kiln, which you can see on the left side is where the limestone are being fed. Then there is a burner where actually it burns the fuel or different kind of fuel are being utilized, and the actual calcination process happens in the middle of the kiln. And finally, you'll see there is a lime that is being produced that comes out of the kiln. So why this problem actually that is being seen in the industry and why it matters? So every plant tries to achieve several goals at a same time or a given point of time. So the main aim we want is to better quality, lower fuel consumption, lower emissions, and higher production. The challenge is that improving one objective often makes another one worse. So it makes one change impacts the other one. So finding the right balance is where machine learning can really help. So what are the current challenges in the kiln operations? Modern plant generate thousands of sensor reading every minute or a second. It's not only plant or each device on a daily basis generates millions or billions of data in every seconds. So operators make many decisions based on these experience or their experience, while product quality is usually confirmed only after laboratory testing. This delay makes it difficult to prevent quality issues before they actually happen, as there is a gap between the process plus the actual data that are being sampled from the machine or the laboratory machine. This is exactly where predictive analytics becomes more valuable. So why this work. While working in the plant, I noticed that similar operating conditions sometimes produce different quality results. Traditional dashboards showed what had already happened in the past, but they could not predict what is the future performance thing, or what are the future attribute value that can be taken into consideration. That raised an important question to me. Can historical plant data help us predict quality before problem occurs? That question became the motivation for this work. So what were the process variables that were being used for the project? We collected historical production data from the plant. This included temperature, fuel flow, airflow production rate, product chemistry, and laboratory quality measurement. It was not limited to these variables, but there were almost 30 to 50, more than 30 to 40 process variables that were taken into consideration. Like many other industrial data sets, the data also contained missing values, sensor noise, and different sampling interval, which required careful preparation. So the ML framework that was being used, the main goal of the machine learning model is very simple: predict product quality earlier, recommend better operating condition, and support operators with data-driven decision. The model is not replacing the operator, so that's the main key point. It's helping them make faster and more informed decision depending on the historical data that has been collected or processed. So starting from the left, you'll see there is a data collection module, data management, machine learning models, different prediction efficiency, performance metrics plus insights, then different dashboard which can be built on top of these production plus the prescription analysis. And then depending on those dashboard plus insights, the operator can take certain action depending on the current, where the current kill resides or the current process variable resides. Instead of optimizing only one variable, machine learning consider many process variables together all together. It helps identify operating conditions that improve quality while reducing fuel uses and emissions. This creates a perfect balance between operational strategy rather than focusing on single performance metric. So what are the business impact that is expected of out of this project? Is it's completely straightforward. The main thing is better product consistency, then lower fuel cost, reduced CO2 emissions or any other emissions that's coming out of the kiln, more stable kiln operations, higher production efficiency. Ultimately, these improvements benefit both the business and the work environment. What were the key lesson learned? One important lesson is that good data is more valuable than complicated algorithms. Another lesson is that machine learning works best when combined with operator experience with or and process knowledge. Collaboration between engineers, operator, and data scientists is the key to successful AI projects. So what can be the future work that can be enhanced if AI is added up? So looking ahead, there are so many exciting opportunities. One of them being the reinforcement learning could enable adaptive process control. Digital twins could simulate different operating conditions. Predictive maintenance and real-time anomaly detection could further improve plant reliability and efficiency of the process. So to conclude, lime kiln operation is the complex industrial process with many interacting variable plus devices. Machine learning gives us the ability to turn these historical production data into useful insight. So by combining AI with human expertise, we can improve product quality, reduce emissions, lower energy consumption, and improve or operate plant more efficiently. So remember the main thing, the main goal is not to replace people, but to give operators better information so they can take better decision by providing them the better insights. Thank you very much for hearing me out. I appreciate your time and I would be happy to answer any questions if you have any. Thank you so much.
Hey, good morning and good afternoon, good evening. Can you see my screen? Can someone confirm on that, please? Awesome. Give me one second. So, good morning. My name is Pramod Salla. I work as an independent researcher, working as a senior software engineer in retail tech domain. Today, I wanted to talk about building autonomous systems that write their own documentation. I wanted to start with something I've seen on most teams that have part over the years, that we all quietly agree that we will write documentation sometime later, and then that later never comes, or it comes at 11 p.m. at night, the day before an audit. Here is the strange part. Our pipelines already hold everything a person needs in order to write release notes. The code diff is there, the pull requests are there, the security scan and Terraform plan are all there. Um, but we are not using that efficiently to write release notes automatically. In the next few slides, I wanted to show you a system that uses all of this information and writes its own documentation. Let me start with the problem. Documentation is not slow because engineers are lazy. It is slow because we are over the years we're able to automate most of the DI CI/CD that includes deploy, test, rollback, build, everything. However, documentation is still done by hand. This cost us in three ways. First, the delay. Second, inconsistency. By that I mean two engineers describe the same kind of change in two different ways, and neither of them is wrong. Third, and this is one thing that is very underrated, we lose what people know when they leave the organization. And then reasons behind those all release leave with them. What stays behind is just the Git log. Before AI, notes by hand, risk checked after the fact, complaints done in a rush at the end. But our system enables pipelines that write their own notes, risk measured automatically, complaints produced all the time. So this is the design. We have five parts and one pipeline. Three of those five parts collect the facts, collect the information about the code changes or discussions that happened around that, and then one part scores them, and then one writes the text. The repository analyzes uses JGit to look closely at the code diffs that are going in that particular release, including how complex the change code is. So we know how much really changed for this particular release, not just how many lines moved. The metadata harvester collects pull request threads, labels, and what the reviewers said. The risk engine counts how many known security problems and looks at how often these components have failed in the past. The FinOps calculator part runs infra cost on the Terraform plan. And the narrative synthesizer built with Lang4j turns all this into a readable text. So we do it in three steps. First step turns a raw data into clear statement of what was meant. Uh, for example, not changed, like let's say we update auth service. It doesn't mention about like auth service was changed, or like let's say so and so XYZ number of lines of code are changed and stuff like that. Instead, it gives out a clear context of that change. Like let's say session timeout behavior or feature is added or changed. The second step adds history. Has this part failed before? What broke the last time someone touched it? What did the reviewers argue about? The third step writes for different readers. Again, in industry, there are various stakeholders that are interested and looks at a different point of view on the same release. If from an engineering POV point of view, we will see like what features or how this is changing the existing product. A product manager wants to know what user will notice at the end of the day. A compliance officer wants proof of checks and who approved them. Now let's look at the numbers. So 89% accuracy in spotting risk deployments before they reach the actual production. Fewer than 8% false alarms and 47% fewer production incidents. I wanted to spend some time here on the false alarm number because I think this is what decides whether a real team keeps using a system like this. A risk check that once you too often gets switched off in about 3 weeks. Everyone has muted an alert channel at some point in time. So being accurate is not just an luxury to have, but it's the a difference between a tool people use and a people finds a workout eventually. I should also be clear about what risk means here because it's a big word. It means two things. We can measure known security problems in parts that changed, weighted by how often these parts have failed before in the production. Let me answer the release quantity or like let's say big, small, medium by just the fit. Someone says this is a big and everyone nods and then we approve it. That is not the measure, that is a feeling. So we give each release a complexity score using Halstead metrics. It is based on the operators and operands in that change code. What matters is that the score goes up as the code gets more varied and more tangled and gives you one number you can compare against your previous releases. That makes four things possible. Release scoring becomes a number instead of a feeling. You can quantitatively measure about that particular release. You can watch complexity rise and fall across sprints, which is something managers cannot see today at all. Release with a high score are sent automatically for a closure review. That that highlights that this is another human in the loop process and not a takeover. And the score feeds back into the risk engine, so the two parts help each other instead of working alone. I wanted to spend some moment on something very valuable in this industry. Those are money and carbon, are both results of code change. We just never show them at the moment the decision is made. I mean at the point of like change is made. So the FinOps calculator reads the Terraform diff and works out how the monthly could bill will change before the PR actually gets much. The tool is not the point, the timing is. A cost surprise found in the next month's bill is an incident, but the same surprise found in a pull request in a normal sprint discussion is just a conversation, and then we can take a route based upon the cost number. We also measure carbon cost of infrastructure changes. The industry is still working out how to measure properly, but my argument is that it belongs in the pipeline as a first class number, and the measure will only get better once we start doing it. And every pull request comes with an automatic cost report. That is the part that changes behavior. We made speed a review topic over last several years, but let's also include money and carbon in the same discussions, and then it deserves the same treatment. Let me talk about how this runs in production, because that is where a lot of promising AI falls down. The language model runs beside a pipeline, not inside it. This is on purpose. If the model is slow, or we hit a rate limit, or the service is down, the documentation gets worse. The build keeps working. Our pipeline should never fail because model had a bad day. Around it, we keep a track of state inside Kubernetes. Long multi-step workflows needed to know what has already been done, and then we hold that in one place instead of spreading it across the pipeline. Then the caching, which reaches 87.4% hit rate. I think it is worth saying that what this or why this number makes sense. Rather than just sounding good in an older code base, most changes looks like changes the system has already described. Similar changes reuse the earlier answer, so the cost stops climbing as the code base grows, which is the opposite of what people fear when they hear language models in the pipeline. Because we are using this cache and reusing it, and then not going for LLM for each of these things. So the results, all of this is measured against the old way, the manual way, done by hand with flexible rules. The number I would point out is not just a single bar. It is that incidents down while deployments went up at the same time. Those two usually pull against each other. Teams either ship faster or break more. Or on the other way, they do slow deployments and stay safe. Moving both the right way suggests we are stopping the right releases rather than slowing everything down. I'll also be clear about the limits.